So question 1, describe the difference between a D latch and a D flip-flop. Who knows this? Yes? Yeah, the only thing I was looking for here was flip-flop edge-triggered, latch is, the D flip-flop is edge-triggered, and a D latch is level-triggered, or level-sensitive. The flip-flop is edge-sensitive, and latch is level-sensitive. All right. Is this circuit a valid sequential circuit? No, because it has a cycle in it that involves only combinational logic. Any questions about that? Okay, number 3, if you can decompose a task into 10 stages that each require 1 clock cycle, so it has a latency of 10 stages per task, and you can achieve a throughput of 5 tasks per cycle, what's the resulting spatial parallelism? For this one, you have to just remember that throughput equals parallelism over latency. Right? Make sense? So the throughput is 5 tasks per cycle. Parallelism is an unknown, and the latency is 10 stages per task. So the parallelism is going to just be 50, right? And the units there are stages per cycle. Okay? Any questions? Okay. So this question, write the Boolean logic for the next state function. So for this, the trick is to be able to match the diagram up with Boolean logic equations. So Q2 prime, which is the next Q2. Now, also, the other thing you have to keep in mind is when you're tracing the next state logic, you have to start with the D input on the register, the flip-flop, and the D input is on the left-hand side. So we have to start from here and work our way backwards. So the D is not something, and it's A, so it's just not A. Right? The next Q1 is going to be Q2 and with A, right? And Q0 prime is a little bit more complicated. This one is going to be Q1 or Q0. Q1 or Q0. And then that ended with A, right. Okay, any questions? Part B was, suppose we set the A input to a constant 1, then pulse the reset, give the first 3 states. So the first state is going to be, when I reset, this reset input is going to set Q2. So if I look at Q2, Q1, Q0, can you see that? Yeah. So at time 0, or at the first cycle, the first state, the Q2 is going to get set. So that's a 1. And then the Q1 and the Q0 are both reset. So it's a 0, 0. And then from that point, we have to look at the next state logic. So at time 1, or cycle 1, that should be cycle. Q2 is just going to be not A. And I said that A is hardwired here to 1. So that means that Q2 is going to be a 0 from this point on forever, right? Because it's not A, right? And A is 1. Q1 is going to be the old Q2, which was 1, and A, which is also 1, so that'll be a 1, right? Everyone see that? So so the state in cycle 1, if it's a function of the current state, you have to go back one cycle, right? So cycle 1, Q2 is 1 and A is 1, so the next Q1 will be 1. You guys with me? Now, by the way, because A is hard-coded to 1, oh, okay, so A is hard-coded to 1, so that means that from now on, Q1 is always going to get whatever was Q2 in the last cycle, right? In the previous cycle. Not last cycle, previous cycle. Okay, and then Q0 is OR of these two, which is 0, and A, which is 1, but 0 and anything is 0, so that'll be a 0 there, right? And then in the next cycle, again, this is locked in at 0. Q2 is locked in at 0 because it's not A, and A is hard-coded. Q1 is going to be Q2, which is 0. That automatically sets that to 0. And by the way, Q1 is kind of locked in now too, right? Oh, no, it's not. No, A is 1, so we're good. But well, it is because Q2 is not A, right? So this is equivalent to saying not A and A, right? So this guy, Q1, is going to stay at 0 from now on. Q0 will be Q1 or Q0, which is a 1, and A, which is a 1, 1 and 1. Everyone with me? Make sense? Let me know if I make a mistake. Okay. Okay, then we have some parameters, and we want to calculate we want to do the setup and hold analysis for this circuit. The setup analysis depends on the propagation delay, right? And the hold time analysis depends on the contamination delay, right? So for the setup is going to be, the analysis is going to be TC, which is the clock, right? The clock must be greater than the propagation delay of the register, I'll just say PR, plus the propagation delay of the logic, plus the setup time of the register, plus the skew, right? So for all three of these data paths, the TC is going to be the same. 2 gigahertz is 500 picoseconds, right? The propagation of the register, which is that's TPCQ, is 100 picoseconds. That'll always be the same for all three data paths. The propagation delay of the logic, that's the one thing that's going to differ depending on which next state logic we're looking at, right? So in order to figure that out, we got to look at well, we don't even have to, I erased the Boolean logic. But looking at these guys, you can see that we're looking at the worst case propagation delay of the logic, right? Well, so this guy only has one gate. And actually, in this case, it has one gate. It comes from A, which is not even from another flip-flop. This one has a path from, Q1. The next Q1 is got one gate delay in it, right? So it's got this gate delay right here, right? From this register through this one gate. And this one goes through 2 gates. So the worst case is 2 gates, right? So we'll just take 2 and multiply that by the logic, which is, what's the gate delay? 100. So it's 2 times 100 plus the setup time of the register, which is fixed 100, and plus the skew, right? So So this is going to be 500 picoseconds must be greater than, this is 1 plus 2 plus 1, that's 400 picoseconds plus skew, meaning that the skew must be less than 500 picoseconds. Sorry, 100 picoseconds, right? Okay. Now, for the other, this would be for the next state for the Q0. This is the worst case, right? So we can't, our skew can't be any more than, or it must be less than 100 picoseconds for the setup time analysis, right? Now we have to do the hold time analysis. And that might give us, that might be easier or harder to achieve. So for the hold, we have the t hold time, right? That must be less, right? Because the hold is a, the hold time, our contamination delay, our total contamination delay must be greater than the hold time, right? And so we need to know the contamination delay of the register, TCR, plus T logic, contamination delay of the logic. What is it, TC? TC, well, TCQ is, this should be, you're right, this should be TCQ. I don't like their abbreviations for that, but TCQ plus TC. Okay, now what do we do with the skew in this case? In this case, the skew would actually be subtracted from this side or added to this side, right? Because the skew is working against us. So we want these two numbers to be large enough to exceed the hold time. But the skew is going to work against us, so that'll be subtracted, right? So the hold time is 110 picoseconds. Must be less than, it's at 20? Yep. Yeah, 20 picoseconds is the contamination delay of the register, and per gate is 10. And we want to find the minimum path for this one. So what is the minimum number of gates? Well, it's going to be 1, right? 1 gate. So 1 gate is in the worst case, so that's going to be 10 picoseconds here, plus, minus skew. And so we're going to have 10 picoseconds must be less than 30 picoseconds minus skew. So skew must be less than 20 picoseconds. So because this number is smaller than the bound that we got for the propagation delay, the setup time analysis, our final answer will be this. This is the because we got to find the smaller of the two constraints, right? So if our skew is 20 picoseconds or above, we'll violate. We may still be okay with regard to our setup time, but we'll violate our hold time constraint. And if our skew is greater than or equal to 200 picosec, or was it 200 or 100? 100, right, for the setup time, then we'll violate our setup time constraints and our hold constraint. Any questions? Okay. Okay, this one, I think I didn't look at, I didn't grade all of them yet, but I think this one went pretty well. The answer to this question is given to you in the question if you read it carefully enough. So it says the elevator must maintain state to track its current floor and its current direction. So that means that there's 2 floors, so it can be on the first floor or second floor, and the direction can be, it could be going up, or it could be going down, or it could be idle. But if you're on the first floor, you can't be going down. And if you're on the second floor, you can't be going up. So that really just leaves, for a 2-story building, that only leaves 2 floors and 2 directions per floor. So there's 4 states. And the structure would look a lot like that traffic light controller. So you'll have a state where I'm on the first floor idle, first floor going up, second floor idle, or second floor going down. And I'll set my reset here. So so we're assuming that when you power this thing up, the elevator will be on the first floor and idle, right? Basically, the idea is that the elevator is determining its position based on what it's done. It's kind of using dead reckoning. It doesn't have a sensor that tells it what floor it's on, but if it knows it starts up on the first floor and it keeps track of when it goes up or down, then it always knows where it is. That's the whole idea of this controller. So if I'm idle, my output is 0. If I'm going up, then my go up is going to be 1. If I'm going down, my go down is going to be 1. And notice I put those outputs, I associate those outputs with the states, not the transitions, because this is it says to design this as a Moore machine. And then what would cause me to go up? Well, from idle on the first floor. Well, it would have to be, I would have to get a second floor request down. So F2 request down. I'd have to get one of those signals, or I would have to get a button from inside the elevator that says to go to floor 2. Right? So this would be an OR. Right? Likewise, if I'm on the second floor and I'm idle, I would only go down if my first floor request down or my floor 1 button were pushed. Right? And then if I'm going up, then I'm going to get to the second floor, right? So I can unconditionally, it said in the question that it takes 1 cycle to actually move floors. So I can unconditionally go from there to there, and likewise I can unconditionally go from there to there. And that's it. Any questions? Oh, and there's an implied loop back too, by the way. So I'm using some shorthand here. If this expression is true, I'll transition. If it's not, I'll loop back otherwise. So else I'll loop back. Right. And likewise, go down is 0 here, go up is 0 here, and go up and is 0, and go down is 0, and go up is 0, and go down is 0 when you're idle. Okay? Any questions about that? Okay. All right, so moving on. Your system is running at 2 gigahertz, and you have a sampling flip-flop. You guys good with this? Erase this. Okay. Okay, so I always memorize the. What's that? Okay. By the way, the answers are on the Dropbox. By the way, in case you want to, if you want a hard copy. So the probability of failure is T0 over Tc times e to the negative. This would be Tc minus T setup over tau. And the only thing I forgot here is n. N goes up there like that, right? But in this case, n is 1. The mean time between failures is the reciprocal of that. So it's going to be Tc divided by n T0 times e to the Tc minus T setup. Oh, sorry. No, that's right. Yeah, Tc minus T setup over tau. Okay? So Tc is what? What's Tc? 2 gigahertz, 500 picoseconds. So 500 e negative 12. N is 1. T0 is what? 60 picoseconds, which is 60 e negative 12. E is the sign. I'm using scientific notation here. Times e. Tc again is 500 e negative 12 minus t setup, which is 50 picoseconds, 50 e negative 12 over tau, which is tau is 50 picoseconds, 50 e negative 12. Make sense? So the setup time, yes, this is 60. This is a 1. Sorry, this is 1 times 60 because n is 1. T0 is 60, tau is 50, t setup is 50. Okay? I don't know. I don't remember what the final answer is. It was. If you go to Dropbox, I've got it posted there under Exam 2 Solutions. 18.8 hours.
I think I got something around that.
Okay. Any questions? Yeah, especially if you got even if you just wrote the equation down without calculating it, it's full credit. Okay. All right, next one is consider the following FSM design. Assume the state variable is named S1, S0. So the first question here is write the truth table. So the truth table here is, first of all, how many rows? Well, the truth table for this is going to be 2 bits for the current state and 1 bit for the input. So 2 to the 3rd power, 8 rows, right? So I need S1, S0, and A, and then I need the next S1, the next S0. 0, 0, 0, 0, 1, 1, 1, 1. 0, 0, 1, 1, 0, 0, 1, 1. 0, 1, 0, 1, 0, 1, 0, 1. All right, so so each one of these transitions represents a row in this table, right? So if I'm in 0, 0, and I get if I'm in 0, 0, which means I'm in one of these 2 rows, right? And I get a 0 for A, then I'm going to stay in 0, 0. Right? If I get a 1 for A, then I'm going to go to 0, 1. If I'm in 0, 1, which is these next 2 rows, and I get a not A, I'm going to go to 1, 0. So if A is 0, I'm going to go to 1, 0. And if A is true, I'm going to go back to 0, 0. Everyone with me so far? Let me put lines here. OK, if I'm in 1, 0, and I get a not A, then I go to 1, 1. So 1, 1. If I'm in 1, 0, and I get a true A, I go to 0, 1. And if I'm in 1, 1, and I get a not A, I go back to 0, 0. And if I get a true A, I go back to 1, 0. There it is. Any questions? OK, so next is the output logic. Output logic is, this is a Moore machine. I know that because the output is inside the state. So S1, S0, No, only current state for output logic. So this one's pretty easy. It's pretty much just 0, 0, 0, 1, right? Because the only time A is 1 is in the 1, 1 state. Right. Okay, so that's the output. And then we get the timing diagram. This timing diagram is asking you, if you start out in state 0, 0, what is the next 1, 2, 3, 4, 5, 6, 7, 8 cycles? How do you transit? What are the next 8 states, right? So, so if I start out in, I'll just do the same thing I did last time. I'll have cycle and state. So in cycle 0, I start in 0, 0. Cycle 1, where do I go? Well, it depends on A. What's A? A is, well, A is kind of, it's unclear because A is changing on the rising edge of the clock, right? Make sense, right? So we're going to sample, we're going to change states on the rising edge of the clock, but yet A is changing on the rising edge of the clock at the exact same time. So which A do I use? Do I use the one that came before or the one that came after? In general, use the one that came before, right? But it doesn't matter. If you use the one that came after, I'll accept either one. So let's assume that we're going to see A as being 0, right? In other words, I get the clock edge. What is A? I know the state is 0, 0. My A is 0. So where do I go? Well, if I'm in 0, 0 and I get a 0, then I loop around, right? I stay in 0, 0. Right. Actually, it would be helpful if I had a column here for A, too. Let's see. Yeah, let me put A. So A is 0 in the first cycle, right? And then it's 1, 0, 1, 0, 0. So it's 1, 0, 1, 0, 0, 1, and then 0, 0. Okay, thank you. 0, 0. Two, 3, 4, 5, 6, 7, 8. Now you might be wondering, why am I using a table when this is a timing diagram? It's the same thing. The only difference is the timing diagram goes from left to right, and a table goes from top to bottom. But fundamentally, it's the same idea. As a matter of fact, when you simulate a design, most simulators will, usually they present the data to you as a timing diagram, but alternatively, you can list them as a table too. In fact, logic analyzers do that as well. If you buy an actual logic analyzer, an instrument that you put on a workbench and connect it to a circuit, they generally have both views as well. Most people use a timing diagram because the time is consistent here, whereas over here, generally a listing will just show you when things change. So in other words, the flow of time is not necessarily constant as you go from top to bottom, but over here it is because there's a fixed axis for time. You guys with me? But in this case, the only thing that's changing is the clock. Everything just changes once per clock, so it's convenient to show it as a table. Okay, so if I'm in 0, 0 and I get a 1 for A, where do I go? Go to 0, 1. See? I take this transition. So I go to 0, 1. And if I'm in 0, 1 and I have a 0 for A, I go to 1, 0. And if I'm in 1, 0 and I have a 1 for A, I go back to 0, 1. And if I'm in 0, 1 and I get a 0 for A, go back to 1, 0. And if I'm in 1, 0 and I get a 0 for A, I go to 1, 1. And if I'm in 1, 1 and I have a 1 for A, I go back to 1, 0. And if I'm in 1, 0 and I got a 0, Then I go to 1, 1 again. There you go. And you just fill those values in your timing diagram. You just fill those into these squares, these little things here. Any questions?
So is the output just off by a cycle?
The output is off by a cycle, yeah. Yes?
I didn't pay attention to the last, but what I did was I looked at the clock. I mean, I didn't look at the clock because the clock was resetting it every edge. So all I looked at was the A and the state. So for the second one, I would get 0. I was looking at the one at the top, like up top, at the diagram. And if it was a 0, 0, then I would just move to whatever the next one is, right?
Yeah, you could use the you could have done it off the timing diagram too. Like I said, this is the same thing as this. The only reason I use this is because I didn't want to reproduce the timing diagram on the board. But yeah, you could just fill them in from left to right, and all you have to do there. Actually, it's easier with the timing diagram because, well, kind of. You just look at this. You look at 0, 0, and you look at A right above it, right? So 0, 0 with a 0A, 0, 0, 0, 0 with a 1A. 0, 1, right? So it's probably a little even more convenient to use the timing diagram because in that case you're matching two values that are right on top of each other, right? Or one's on top of the other, right? You don't have to worry about the clock. You just, because the clock is, basically one clock cycle per division there. All right, any other questions about that? Okay, good. Like I said, the answers are online, and we'll have your grades. Some of you already have grades posted, the ones that are entered, but the rest of the grades will be posted certainly by the end of the week, and we'll have the exams passed back on Monday. Okay, so now we can start the stuff that I think is the most interesting part of this class, is hardware description language. So far we've designed circuits using a truth table to describe their behavior, right? Or sometimes a Boolean logic, or sometimes a finite state machine. That describes the behavior, right? And then we convert that behavior to a circuit. How do we do that? We just kind of do it by hand, right? We look at the logic, and then we match up each logic operation. We put a gate, we draw a gate, and then we connect the wires according to the variables, the literals that are being computed on, right? You guys with me? Right? So you guys did this, we did this in this class, you guys did it also in 211, but you guys also know that chips have like hundreds of millions of gates, right? And you also know that truth tables grow exponentially as you add inputs, right? So you probably have been thinking that all of the methodologies that I've taught you are basically useless. They don't scale to any circuit of any practical size, right? None of the things that we've done in class will ever are not usable to build an actual chip, an actual product, any kind of realistic practical circuit. Now, we teach them because you have to understand the basics, but if you really want to design a processor or any kind of chip, you're not going to be using any of the stuff that you've learned so far in this class. You're going to have to come up with a completely different methodology for doing the design. And that's what hardware description is all about, hardware description language is. But the problem with it is that there is a fundamental thing about HDL that makes it hard to learn, is that hardware description language is a high-level language. It's like Java or C or Python. But you're generating hardware from it. So when you compile it, they don't call it compiling with HDL, they call it synthesis. Because you take the program and you're converting it into gates and registers, right? But the gates and registers don't behave like a high-level language. A high-level language has concurrent semantics, meaning that when you run a high-level language program, you guys are taught that when you're running a program, the program has a state in which in which the computer is on one line of code at a time, right? Does that make sense? Right? When you run a Java program, as the program is executing, the computer that's executing it is executing it at a specific point inside the program, and only one point inside the program. Or if we taught parallel programming, which we don't, but if we did, you might learn that, well, you could be at different points in the program if you have different threads, right? But how many threads do you have? Well, it's limited by the number of processor cores you have. So 4, 8, 12, something like that, right? So it's still, you're at only certain points in your program at one time. But that's not how circuits work. Circuits are fundamentally concurrent. When you draw a circuit diagram, there's no notion of a program counter. There's no notion of where the computer is in the code. Every single line of code, every circuit, every wire, every gate is all executing concurrently. All of it. The whole thing is executing at the same time. It uses concurrent semantics. Make sense? Which means that if you have an HDL program, the order of lines in the program doesn't mean anything at all. Whereas if you write a Java or a Python program, the order of lines is of critical importance, right? Because if you take a Python program and you randomly scramble the lines, it won't work anymore. But with an HDL program, it will, because every line executes concurrently, just like every wire executes concurrently in a Boolean logic circuit. You guys with me? The other problem is hardware description language is a high-level language. You write it like a high-level language in a text editor, just like you do Java or Python. But as you write it, you have to think about the circuit that it will generate when you synthesize it. So when you have to write it, you may have to write it in a way that's pipelined, where you're breaking things up into multiple cycles, or you're cognizant of the path delays. How long of a data path will this generate? Will it execute my, or will it exceed my setup time constraint? That kind of stuff. You have to think about these things as you're writing it, but there's this fundamental disconnect between writing code and thinking about what circuit it generates. And unfortunately, that's something that you just have to get good at. That's just a skill. It's something you have to learn through practice to understand how you can visualize what the circuit looks like as you write the HDL code. Everyone with me? Okay, so that's the challenge. The other thing that's kind of interesting is that there's lots of programming languages, and programming languages come and go, right? When I was in school, when I was in undergraduate school, Python didn't exist. It didn't exist when I was in graduate school, as a matter of fact.
Wasn't it like Lotus was like one of the first ones?
Well, there was the really old ones. There was like Ada and Pascal and COBOL and those kind of things. And then over time, programming languages come and go. The C and C++ have kind of persisted for a long time. But Perl came and went, and Python is hot now, and Go is coming, and Rust is coming, and there's lots of programming languages, but HDLs pretty much only two. There have been other HDLs that have come out, like BlueSpec and a few other ones, but by far, Verilog and VHDL were developed in the 80s and still are 99% of the market in HDLs, right? New HDLs have historically not been able to catch on. Why is that? I don't know. I don't know if anyone knows. System Verilog is the older of the two. Oh, sorry, that's not, is that true? Yeah, VHDL came first, right, sorry. VHDL stands for VISIC Hardware Description Language, and VISIC is another acronym, is an embedded acronym that means Very High Speed Integrated Circuit. So VHDL stands for Very High Speed Integrated Circuit Hardware Description Language. It's got a nested acronym in it. This is kind of a neat history. VHDL came out, I don't want to go on too long, but VHDL came out as a way for the Defense Department to have a way that they could specify the behavior of chips that they're ordering from defense contractors. So prior to this, they would go out to a defense contractor and say, yeah, I need a chip that it can calculate ballistic trajectories for a tank cannon, and it should do it. It should give me an answer within 200 nanoseconds, and it shouldn't run. It should, and so sort of they would have to formulate the specs as English prose, right? The problem is that, of course, as you might imagine, it's hard to accurately capture the behavior of a complex system with English prose, because English is just not a precise way to describe something. So they developed Vhdl as a way to essentially specify the behavior of something through a program, right? And that way you could take that program and you could run a simulator on it, and it would simulate the circuit even though it might not exist yet. Like, so they could say, well, this is how it should behave. I'm going to give this requirements to you in this language, and then you can run it in a simulator on a virtual version of this chip that doesn't even exist yet. And then when you make the chip, then we can compare the output of that chip as compared to what the model, the virtual version of it predicts. You guys with me? So that was kind of the idea. And then eventually they came out with tools that allowed you to take the description and to synthesize it. So you could just write the description, hit a button, and boom, a chip will pop out. That's called synthesis. That came later, though, right? The problem with VHDL, and I used to teach this class in VHDL, I switched it to Verilog. VHDL is based on Ada. So there's all these programming languages that are descendants of Ada. Ada is one of the earliest programming languages and still used by NASA, and it's still a useful language. But it's very old. And so Pascal and VHDL and a bunch of these languages that are case insensitive and very verbose derived from Ada. COBOL, I think, came from Ada, right? I think even Fortran came from Ada. There's all these languages, and basically you can tell any language that comes from Ada, you can identify it immediately because, like, when you declare a function, you have to type out function. And when you declare an array, you have to type out array. And instead of just saying, and then you have to say, to specify the array bounds, you have to say 10 down to 0, right? So Ada was designed to be very readable. It was designed to be self-documenting, and VHDL is the same way. The problem is if you type that out, a language like that, it's obnoxious as hell because you gotta do 10 times the number of keystrokes than you need to type in your code. So the advantage is that you can read it easily. The disadvantage is it takes forever to write because there's so much unnecessary typing you have to do. Verilog was designed as a solution to that, and Verilog looks more like C and Java. It's case sensitive and almost impossible to read because it's very sparse. The code is very concise. Nothing is spelled out, and it's very, looking at a Verilog code, you have no idea what's going on. It's very hard to read, just like C is. So that's the difference. So what is the market share here? About half-half. But I've learned in the last 10 or 15 years, I've seen Verilog seems to be, the trend I've seen is that Verilog is used mostly in industry. VHDL is used a lot in academia. So we teach classes in our department with the kind of the presumption that we're teaching you to go out into industry. Most of you are not going to become professors and work in a research lab. So as a result, philosophically, I thought it would be a better idea to switch from VHDL to Verilog, and that's what I did. The nice thing, though, is your book, your textbook, is one of the reasons I picked this textbook is because it does both. In fact, it shows every example side by side, VHDL and Verilog. So not only does it teach both languages, but you can actually, every single example allows you to compare the syntax of both, right? The other nice thing about these two languages is that if you know one, you can easily pick up the other once you learn about concurrent semantics. And also, they're interoperable. If you design something in Verilog and design something in VHDL, you can plug them in and simulate them and synthesize them together. They're completely interchangeable with every CAD tool out there. So it doesn't really matter which one you learn. But we're going to learn Verilog. Verilog, by the way, is called System Verilog now, which is I hate that name because it's unnecessarily long. But System Verilog is the latest version of Verilog. It's the latest spec, and they added They added some stuff to it and they renamed it System Verilog, but I'll just call it Verilog. Okay? Yes? No. I will have snippets that'll ask you to write out in the tests and in the quizzes, but or in the tests. I don't know about the quizzes, but no projects. No, we used to do this class entirely as projects, but it became impractical with this size class. But it's okay because we're still going to cover the language just as well as I did before. Okay, so I mentioned so there's simulation and synthesis. The other thing about this stuff, by the way, is the HDL is not open source friendly. There are historically, if you wanted to use either one of these, you had to buy thousands of dollars of commercial software. Recently, only recently, are there now some open source stuff. But even then, it's mostly just simulators. I don't think I've ever seen an open source tool that can do synthesis. Synthesis is where, so just to clarify this, if you write a program in, I shouldn't say program, if you design something in Verilog or Verilog or VHDL, you can simulate it, and it'll give you a waveform just like we had in the last test, right? That's the way you tell if it's working, and debug it if necessary. But at some point, you're going to be like, oh, this thing's working, time to generate hardware. Then you do synthesis, and that converts your program into gates, into wires and gates, right? I don't think there's any way to do this for free. This costs big bucks. Simulation, there's a tool that came out a few years ago called Icarus Verilog, which is actually the tool I used to generate that waveform that was on the test. And there's another one called Verilator now that's even more popular than Icarus Verilog. Verilator is kind of cool because it's kind of a different methodology. Verilator, instead of simulating, it converts your code into a simulator. You actually compile your Verilog into an executable file and you run it, and then it behaves like the simulator would. So it doesn't have a separate simulation engine, which is kind of a subtlety. But anyway, most people use Verilator now, the open source people. In this class, we used to use another tool called Modelsim, which is commercial, and we still have a license for that. And then the synthesis, you can either synthesis to a programmable logic device or to an ASIC. But again, this is something you got to pay for. No one in the open source community is skillful enough to do a free synthesis tool. As far as I know, anyway. At least nothing that targets a modern technology. Okay, so how do you write Verilog? Well, the first thing you have to understand is there's two types of coding styles in Verilog and VHDL. There's behavioral and structural. Behavioral is when you're writing code that implements a truth table or a state machine. You guys with me? Because ultimately, that's the only thing hardware can do, is a truth table or a state machine. Those are the only two functions that digital logic can perform. So in chapter 2 and 3, you guys learned everything that digital logic hardware can do. Now the question is, how do you design large-scale systems? So behavioral logic is stuff that ultimately is a truth table or a state machine. Structural is when you have pre-made modules and you instantiate them and connect them together. So structural Verilog is another word for building a schematic. Schematic is you got objects that are connected, that are interrelated, right? Also called a netlist or a block diagram. You guys with me? Most code you write in Verilog is structural. Probably 90 to 99% of it. You very rarely are writing behavioral code. In most cases, because behavioral code is when you're at the leaves, when you're designing the low levels. But once you've got a basic library of components built up, at that point you're just assembling them together, and that's behavioral code. So most of the time you spend is in behavioral code. Here's an example. So this is a module. So wait, let me back up here a second. One more thing. So structural structural code is based on modules. You have these things, you design a module that does something, and then that module serves as a tool, as a component that you can assemble together using structural Verilog into another design that's built with submodules, that's built with modules. You guys with me? So you have this design hierarchy. I used to have a slide for that. I want to switch to the textbook slides. I lost that one. So a hierarchy is where you have, you guys know about full adders, right? You learn about, we covered full adders in this class. So when you build an adder, you build it from full adders. So you build the full adder first, which is behavioral modules, because it's that little truth table that makes a full adder. But then what do? You take a bunch of full adders and you put a bunch of them together to make a big adder, right? So that's kind of, that represents the hierarchy. Now once you have an adder, then you can take an adder and use it to build with other components and build a floating point adder. And once you have a floating point adder, you can take multiple floating point adders and assemble them together into a vector unit or a SIMD unit. And once you have that, you can take that and use it to build a CPU. And once you have a CPU, you can use that to build a multi-core CPU, right? So all of the stuff there is built hierarchically, where mostly you're taking modules that are simpler and assembling them together into something that's more complex. So a lot of the design is based around that notion. So here's an example module to show you the syntax. This is a behavioral module. This module is called example. And by the way, you can think of this as a class almost. This is analogous to a class in Java. So you have a module, you give it a name, and then you provide the inputs and outputs to the module. And then you end that with a semicolon. And then you have end module. And then the module description is in between. Make sense? Now the first thing you probably notice from this is, where's the curly braces? There's no curly braces in Verilog. There is, but they're not used to define scope. They're used for bit twiddling, which I'll get to in a minute. But there's no curly braces that define the basic blocks in this language. Kind of weird, right? Module and end module is what defines the beginning and end. And also there's a semicolon after the module line. That's kind of weird, right? You don't do that in Java. You don't do that in C++. You don't put a semicolon there. That's kind of weird. Also, no semicolon here. I don't get it.
I mean, it kind of looks like stuff that something that you would do in MATLAB. But
Yes, it's very similar to MATLAB. And that's the problem, is that in MATLAB, when you index an array, you use parentheses, and in Verilog, you use square brackets. And that endlessly, I always use the wrong one because I use MATLAB. Write in MATLAB and in Verilog, and it's actually, if you know MATLAB, this is very similar to MATLAB. Yeah, that's a good point. I'm glad you brought that up. Okay, so anyway, what does this do? There's one line of code in there that says assign y, not a and b. Not A and not B and not C, or blah, 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 blah. So this is a Boolean logic expression, but it's written in the style of Java. A bitwise not is a tilde, or is a bar, and is an ampersand. So this looks like Java now, right? This part looks like Java, but this is defining a Boolean equation, and A, B, and C are single bits, and Y is a single bit. Yeah, question?
Is that assigning y to equal 1 whenever those?
Yes, that's right. So this is treated like a Boolean equation, sum of products, and when it's either 1 or 0, true or false.
Okay.
Every one of these is 1 or 0. What can I say? What else can I say about this? There's an assign. This is called a concurrent assignment statement. Now, this is a bad example because there's only one line of code. But concurrent assignment statements are concurrent. And what that means is whenever any of the things on the right-hand side, you have to think of this, by the way, you have to think of this as the hardware it generates. And so this is creating a circuit in which A, B, and C are the inputs and Y is the output. And you know that because A, B, and C are on the right-hand side of the equal sign and Y is on the left-hand side. So anything on the right-hand side is an input, Anything on the left-hand side is an output, which has some implications. The first is that any of the things on the right-hand side are treated as a sensitivity list, meaning that if the state of any of these signals changes, Y will be updated immediately. It doesn't wait until the computer gets to that line of code. It happens immediately. This turns into an event-driven network where if any of the inputs change, the output, this statement is activated when any of its inputs is changed. You guys with me? Which is the way that hardware works, right? Because if this is our circuit and any of those changed, it doesn't matter what else is going on, the output will be updated to reflect that. The only difference is in real hardware, it would happen after the propagation delay, and in here it's going to happen an epsilon time because there's no propagation delays listed, and the Verilog doesn't know what the propagation delay is because that's technology dependent. So this is only behavioral, right? Make sense? Right? Also, Y is an output. And so just like a logic circuit, nothing else can drive Y. No other line of code can set Y. Because if it does, you'll have two gates potentially driving one wire. And if one tries to pull it up and one tries to pull it down, you get a short circuit and your chip blows up. You can't reassign Y like you can in Java. So you have to get that. This is the hardest habit to break because this looks like a high-level language. It is a high-level language, but this is not like Java. You cannot reassign Y here. If you have any line of code, any other line of code that sets Y, it will short circuit your chip. Yes?
Is it like a global variable or something?
No, it does have scope. There's still a scope. The scope here is that Y is defined within this module as the output here. So there is a scope. Now, if I instantiate that module somewhere else and I connect that Y output to another wire in another level of the hierarchy, it's the same signal, even though it may have different names depending on where you are in the hierarchy. But you can still only have one thing setting it in each module, right?
But it's still accessible by other modules, so you can still.
You can read it by as many things as you want. So you can set Y, you can use Y on the right-hand side in as many lines of code as you want. That represents a fan out. So this Y can be set in fanned out, connected to a bunch of inputs, but it can only be set once. Right.
So even if it's in a different module, then it would still it's not allowed to be.
No, because that Y would be when you're going to set it in here, and then this statement will affect the same signal as connected throughout the hierarchy. Like I said, it may be called, and I'll show you examples of that in a minute here. I'll get to that soon. Okay, sorry, I already talked about that. Okay, so when you simulate this thing, you're going to get something that looks like this. I don't know what generated this. Some simulator. I don't know what they used I don't recognize the graphics here, but we've got A, B, and C, and Y. Notice that they're all treated equally here. It's not clear from this what's the input and what's the output. We don't know. They're all just A, B, C, Y. They're all just equal. They're all just listed as. So that's part of the problem when you simulate this. You don't know what the relationship of these is. You just can see their values here, right? But generally, if I wanted to test this, I would test it by running through every possible value of A, B, and C through it and seeing what Y is, right? So basically, this is kind of like walking through the truth table. So A, B, and C are 0. And then in this case, A is 0, B is 0, C is 1. So C is like the least significant bit here. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So there's all 8 possibilities come through. And again, this is a timing diagram. So in order to evaluate one test case, you have to draw a vertical line to capture what's going on at one moment in time. So if I look at what's going on at 640 nanoseconds here, I'm going to capture that in that moment in time. A is 1, B is 1, and C is 0, and thus Y is 0 because it's based on this Boolean equation. You guys with me? Now you might say, wait, whoa, time out. Who's setting A, B, and C here? We know who's setting Y. this statement is setting Y. Who's setting A, B, and C? I don't know. Somebody. Somebody somewhere. Someone is stimulating A, B, and C. So there's some kind of stimulus that's coming in. Somebody on the outside is setting A, B, and C to this bit pattern. Yes?
Like a parameter, right?
Yeah, they're like parameters. Well, there is a notion of a parameter in Verilog that's a little different. They're kind of like arguments, function arguments, sort of, right, in this sense. But somebody is testing A, B, and C. Someone is exciting A, B, and C, and they're generating this pattern. Okay, then when you synthesize, and this is the part I told you that, as far as I know, I've never seen an open source tool that can do this. Maybe there's something that can do simple ones, but you take this and you convert this to hardware. And so this module, when you synthesize it, gets converted to this, gate level design, also called a netlist. And then this can then be converted to, these gates can then be mapped onto some sort of physical substrate if you wanted to manufacture a chip that did this. Yes?
And is that the lowest amount of gates and everything that you could get?
Not necessarily. That's the other thing, is this a minimal? I don't even know. Well, clearly they minimized it, right? Because the way it looks, there's 1, 2, 3 input AND gates, right? And 1 3 input OR gate here, right? Right? Sum of products, right? This sub-expression can be done with 1 3 input AND gate. This is 1 3 input AND gate. This is 1 3 input AND gate. And this whole thing is 1 3 input OR gate. But yet, not what we got. So they minimized it. They ran this through, they do a Carnot map? Probably not. They used an algorithm called Quine Mccluskey, which kind of is an iterative heuristic that tries to solve the Carnot map for an arbitrary number of inputs. Not necessarily optimal, though, because that would be NP complete. But you'll get something that is minimal. Also, this may be subject to constraints. This is what might come out of the synthesizer, but when I map this onto real hardware, I might find that I don't want to do that because I may not have a 2 input gate that looks like this. So I may have to substitute something else, or I may have to, maybe I want this to be deeper, more gate delays, but smaller gates. There's all kinds of trade-offs, but there's all kinds of ways that you can, there's many ways that you can generate hardware that performs this behavior. This is just one of the ways to do it. I could have used a mux here to do it. I could have used a lookup table. I could have used a full gates. Lots of options here. This is just only one way to do it. Okay, a couple of things about Verilog is that it is case sensitive. You might say every language is case sensitive. What are you talking about? Yeah, every language you guys learned is. But that wasn't always, Vhdl is not case sensitive. Neither is Ada or Pascal or COBOL or Fortran. This one's case sensitive, but it should be familiar, right? Names can't start with numbers, I think, is a pretty common restriction. White space is ignored, also very common. And comments are the same style as C and C++, where you've got block and stream comments. Same syntax. Okay, so here's some structural Verilog for you. So here's an AND gate and an OR gate module that are defined in a similar way as I defined the other one, the other guy. You guys with me? So these guys have inputs and outputs. I like to think of these as formal arguments. You guys learn about formal and actual arguments? I like to think of them as formal arguments, but they're really an I/O. These are really I/O specs. These are pins, input-output pins. But I like to think of them as formal arguments because when you instantiate these into a more complex module, you have actual arguments that connect into them, which ends up changing the names of things depending on where you are, depending on what your context is, what your perspective is. What do I mean by that? AND has ABC input, output Y. Inverter has an A input and a Y output. So I want to now I want to put these together. I want to instantiate an AND. Think of it like this is a class and I want to create an object for it. So I want to create an AND, I want to plop an AND down, and I want to plop an inverter down, and I want to feed the output of the AND into the input of the inverter, right? So to do that, you have to first create an internal signal called N1. The type is called logic. These are also logic, by the way. Logic just means bits. By the way, I'm going to address this later, but what's a bit? Bit is a data type that can store 1 or 0, right? But remember, I think I covered in chapter 1 or 2, there's other values for bits. There's undefined as an X, remember those? There's a don't care, right? So there's other bits. It's not actually, these are bits, but they're not binary. They can take on other sort of special values between 0 and 1. But I'll get to that in a minute, a little bit more, get into more detail. There's a logic N1, and so here's where things get confusing. I create an AND gate. First of all, the syntax here is very similar to Java. I put AND3 first, because that's the type, right? Then I say AND gate, right? Here's the problem with this, by the way. I called it AND gate, but I will never use this name ever. It forces you to give names to these things. But the only place you'll ever see these is when you simulate. Like when you simulate it, you'll see the names in terms of the hierarchy. But you'll never refer to this in Verilog. You'll never refer to this name in the Verilog code. If there's a way to do it, I've never seen a use case of that. So the point is, you can call this anything you want. It's not really that important. The only time it comes into play is when you're simulating. A, B, and C are the inputs, and then N1 is the output. Now you might say, well, how do you know that? Well, it's the ordering. It's the same way in Java. I'm going to list A, B, and C, and then N1, and based on the ordering of those, N1 is the output Y. But here's the problem. Now I've renamed it. It's called N1 here, it's called Y in here. So if I'm in here, it's called N1. If I'm in here, it's called Y. It depends on where you're looking at the signal in the hierarchy. Then N1 is going to then connect to the input of the inverter, so it shows up in position 1. So inside the inverter now, if I'm in here, I've got A. If I'm in here, I've got N1, but it's the same signal with 2 different names. Just depends on where you're looking at it from, right? And because I use the same name for the output of this and the input of this one, they are now connected with a wire. So I have effectively drawn a wire connecting the output of AND3 to the input of the inverter simply because I have an internal signal and I have the same name that connects to both as the actual argument. You guys with me on this? So this is very common. This is the way, if you guys have, I don't know if you guys use SPICE in your circuits class, but SPICE uses the same idea.
Yeah.
When you do a SPICE net list, it works exactly the same way. Wires are connected through common signal names, right? Any questions about that? Okay, so this is behavioral. Why? Because there's a truth table, Boolean logic. Behavioral, this is structural code. Structural because there's no behavior in here. I just took 2 gates and connected them together. So this is structural code. Like I said, most code you write will look like this. Okay. All right, so what about multi-bit signal? So you can also, this is the thing, this is where you're going to get in trouble if you're used to MATLAB. And this is also kind of strange. This also differs from C and every other programming language. If you have a multi-bit signal, you treat it like an array, right? So that way you can address the individual bits of a signal. You guys with me? Like array elements. So in other words, you have an array of bits, right? The problem is that when you declare an array of bits in Verilog, you have to put, first of all, you just don't put the size like you do in every other language. You have to put the range, 3:0, 3 down to 0. It means that's a 4-bit signal. This takes a while to get used to, by the way, because you guys are used to saying array of 4, declare it with 4. But every time you declare an array in Verilog, you have to think about, well, what's the size of the array? It's 10. Okay, 9 down to 0. Every time you declare an array, you have to subtract 1 from the size of the array and then and then put that number in and then say :0. You guys with me? By the way, the :0 is totally redundant because you'll never declare anything that has anything other than :0 in it.
Is it invalid to do so, or is it just not?
I think you can. I've never seen anyone do that, though.
So you,
Don't know what the point of it is. You can index. Now, when you index, like if you want to slice bits out of an array, then you will do that. Like you'll say, oh, I want bits. You might say, I want bits 3 down to 2 from this, meaning I want the 2 most significant bits. But when you declare something, when you declare a version, you'll always have :0. So it's a lot of needless typing, complete waste. But it requires you to do that all the time. So anyway, notice also that that comes before the names of the variables instead of after, like in Java, in C, in MATLAB, Python. Well, MATLAB, you don't have to declare variables, but you guys with me? Okay, so what does this mean? It means I have 2 4-input inputs, and I have 1, 2, 3, 4, 5 4-input outputs. You might say, wait a second, what do you mean by 2? You only specify the size once. Yeah, because this size is applied to everything that comes after it. This is a shorthand where if you say input logic 3 down to 0, that applies to the A and the B. You guys with me? Okay, and then that's pretty much it, because then I can do things like I can say A and B, and this actually ends up becoming a 4-bit AND operation. So you end up with a design that looks like this, where you have all these 4-bit wires running everywhere. Well, they're not wires, they're 4-bit. We used to call them buses, but they're 4-bit signals. Okay, that's all I've got for today. I will continue on Monday.